So this is a recent research project I did together with my student Tianxin Tang and also Bogdan Varinsky from University of Bristol. So let me give you a quick toy motivating example. Let's say we have a database of people's records stored on some server, probably on a cloud, and we want to query it. Let's say I want to get some information on my co-author, and I would just query it by name. I will get my friend's record. For those who know Bogdan, it's not quite his photo, but let's pretend it as it's. He didn't give me a photo of himself, so I have to use something else. With modern technology like Google Photos, you can even search by photo, and you should also be able to retrieve the record. Also, what's useful is what's known fuzzy search or similarity search. If you make a typo, a small typo, and we know it from Google searches, you should also be able to retrieve the record. And also with modern technology, you can even search by similar photos. Google Photos does an amazing job on that. And even if the photo of the person is slightly different, you still maybe you should be able to retrieve the record, which contains a different photo of the same person. OK, so of course, there may be some privacy issues if data is somewhat sensitive. And in my example, one big issue is that a spammer who compromises the cloud can get very, very easy access to all phones, all the emails right away. Okay? And of course, there are other issues. Of course, researchers looked at this problem. And for example, the searchable encryption primitive can solve the many privacy issues. There, the database is encrypted, the queries are encrypted, and the attacker mention is not possible. So the attacker cannot get easy access about the data or even about the queries. So then what's the problem we are looking at? Well, the problem we observe is that searchable encryption obviously requires the users to have secret keys. It's a primitive which relies on secret keys naturally. But we observe that there may be situations when setting up secret keys is not always possible, because now more often we're working in completely decentralized environments. Like, for example, if we imagine Internet of Things, there are like cameras or sensors collecting lots of data from various sources. It needs to be stored and it needs to be queried by multiple parties. So how to do the key management? And kind of the main issue is not like setting and maintaining keys, but who should have the keys? Because it's not even clear who the data owner is. It's kind of everyone's data. Right? We want everyone to probably submit data and everyone to query it. So it's not clear who should have the authorized access. So we are just thinking, what can we do in this keyless setting? And so our focus is to study the problem of private fuzzy or similarity search in the keyless setting. And you may already think, like, is it even possible? Without secret keys, how can we do any crypto, right? So we'll see. And a little bit more precisely, we study how to mask databases. I may use the term encryption, but I really prefer to use something weaker, like mask or obfuscate database, because we're really not going to use secret keys. So the users who know what they're looking for, they should be able to retrieve the associated information. But the attacker who possibly compromises the database cannot do easy mass harvesting or data mining. And data mining, I'm not saying it's a bad thing, but sometimes we don't want the data to be analyzed. So the spammer shouldn't easily get access to everything. And we focus on the keyless setting. Even more in detail, so we propose a concept of keyless fuzzy search. So as I said, the user can query a masked database, retrieve its parts, get the replies from the server, decrypt the content only if the user possesses some information which is close to the encrypted data. But an attacker who really wants to retrieve the information, it has to come up with the right queries. But if the data has some entropy, then this may be costly. And that's kind of the intuition for security we're going for. And you may already sense that we cannot promise great security. Again, we're working in the keyless setting. So it's just the attacker, we want the attacker to do more work. We don't want it to have very easy access. And it may make sense for some data sets where data has some entropy. We'll talk about this. So the security guarantees cannot be strong, but we want them to be well-defined, and we want later to see when it makes sense or not. So I already mentioned searchable encryption. The goal is somewhat similar, but keys are required there. Fuzzy extractors and fuzzy vaults are a related notion where we want to extract randomness from similar data, but it's not immediately clear how to do search with this primitive. So it doesn't fit exactly, but we will use it as one building block. Message-locked encryption, or MLE, it's similar. It's because it's also a keyless primitive, but it only works for exact match, and we want to consider similarity. And it's used mainly for data deduplication, so it's somewhat a different goal for this primitive. But our thing can be viewed as like fuzzy MLE. And the most direct, the most related primitive is obfuscated database by Naranyan and Shmatikov, which have the exact same goal, but the solution is much, much simpler because they only needed to work it for the exact match and didn't consider similarity search. Okay? So there are more potential applications. None of them are like exactly perfect. That's something we think our primitive will be useful to. For example, so self-driving cars, they're collected, their sensors like recording and photographing the environment, and this can be matched against some other public data. Not everything should be public because there are people on the street and so forth. You only want to match something where the car is. And similar for the vision-based navigation of drones and such. When GPS is not available, they do navigate by what they see, and they match the recordings against public images with the maps. And again, it makes sense only to overlap those which are needed, to do like search on the need basis. Sharing, network measurements, people may not be even willing to share network measurements because there is some privacy issue, but it's needed for the diagnostics to identify clusters of similar problems and such, so our primitive may help. Also, we didn't consider it closely, but for example, searching for relatives with your DNA. So here we're also talking about genomes, DNAs have a lot of entropy, and if I just want to retrieve my relatives, so our primitives can search. But again, maybe our security may not be strong enough, and I think there will be another talk for the same goal with better security. Okay, so contributions or overview. What we do, we searched for efficient schemes, and we propose two general schemes, and using different techniques, slightly different techniques, and one scheme specifically is suited for image search. Okay, so we want to do proper security analysis. As unusual in crypto, what we need to do first, we need to define the primitive, what kind of scheme we're looking for. Then we want to have a formal definition of security describing what attackers can do and what they shouldn't do, when is it a break, and then we wanted to have proofs of security. So the first thing is we had to think about the security. We had to think about how to define security. And we propose a formal security definition, and this is just the intuition here. So we ask a scheme not to leak any information about the data and the queries, except for some well-defined leakage function. And because no efficient search is possible if no information is leaked. And this is the common approach to defining security for searchable encryption schemes. Since we're dealing with fuzzy similarity search, we need some notion of similar data. And so we define a closeness domain, just some domain with the closeness function, which just define whether 2 points are close or not close. And this can be done for common metrics, Hamming distance, Euclidean distance, and so, but we define it very generally. And we say that Achilles fuzzy search scheme, if you want to design it, you have to design several algorithms: how initialization algorithm, encryption, decryption, how to query, how the server will index the data, and how it will answer the queries. So again, this is not about security. This is not how a scheme works. This is just what do we want from a scheme in terms of inputs and outputs. So the scheme may have the initialization algorithm, which will just create some public parameters, and the user will use them. Then, to encrypt the data initially, the user will run the encryption algorithm, and it will take a message, which is like here it's like the whole record in my toy example. And the access data is the searchable parameter, whether it's the name or whether it's the photo. And the output will be a ciphertext, which the server will store and possibly index somehow, create some data structure which may help it search efficiently later. And later, the user will want to query the data. That's why we need the query algorithm, which will take the query data, again, the name or the photo, and the public parameters, and the output will be the tag or the query, which can be sent to the server. And the server will match it against the database and find the related ciphertext, which match the tag. And the user should be able to run the decryption algorithm, should be able to decrypt, and the input would be the access data, which normally will be exactly what the query data. If I search by a photo, I should be able to decrypt with that photo, and I should get the associated record. Okay? And we want such a scheme to be correct, meaning that if I query, I should get all or at least most of the data which contains the information close to what I'm searching for, and I should be able to decrypt. Okay? Okay, so this is just the syntax. I'll tell you later what the actual constructions are, but we still need to define security. And for security, okay, so the intuition, I already mentioned this, but here it's a little bit more closely. So the attacker has to make the right query to retrieve the information. If the data is hard to predict, but since we're looking at similarity queries, the notion is closeness unpredictable, then we would say that no information is leaked besides some well-defined leakage function. And this degree of closeness and predictability will be a parameter. So I'll tell you. And so more precisely, we have two experiments, the real and the ideal experiment. In the real experiment, the adversary is given the ciphertexts and the queries and has to guess some information about the underlying plaintext. And in the ideal experiment, the adversary is not given the ciphertext. It's just given the leakage function and has to guess also the information about the plaintext. And the level of security is really depends on how much better the real adversary does than the ideal. So that's the real experiment. The attacker, we have some sampler which produces messages, access data, and queries. And messages are encrypted, queries are produced. The attacker is given everything the real attacker sees, the ciphertext and the queries. And it has to guess some information about the messages and the queries, which was set in the beginning. So that's in the reality, right? The attacker is trying to guess something useful. And then we consider the ideal experiment. And this is ideal adversary, which looks less harmful indeed. So it's not given the ciphertext or the queries. It's only given what is supposed to leak about them. And it still has to guess something about the plaintext. And the intuition here, like, definitely this attacker should not get very much, and we want the ideal attacker to not leak more. So the ciphertext should not leak anything more than what this leakage function leaks. And then the privacy advantage is just the difference between how that real attacker does in real experiment and how the ideal attacker does in the ideal experiment. We not require this advantage to be negligible for schemes, which is common in crypto. It's just because it will really require data to be real closeness and predictable. And that's probably not the case. Really, no one can predict the data unless with really small probability. We leave it as a parameter. Depending on the entropy on the data, you may get a big advantage, but we leave it as this. You really can plug in some estimates for the entropy on the data and then get some bound on the security we will get. Okay, so that's the security definition. Now, the constructions. So the main building block we use in all the constructions are LSH, or locality-sensitive hashing. So this is a very useful primitive, and it's easy to describe. If 2 points are close, then the hashes are likely to be the same. And if 2 points are far, then the hashes are likely to be distinct. And to amplify this likeliness gap, one usually looks at what we call extended LSH, where one extended hash is actually a vector of multiple hashes on the same input. And here is a simple example. For Hamming distance, and here we have two vectors, I and I prime, 2-bit vectors. The LSH is actually projections on few random bits. Here, just like 3 bits we just take. And we consider for each, let's consider 5 hashes, which are the same for both vectors. We're just going to project 3 random bits and look at the results. And you can see that I chose those vectors which are quite close, and therefore a couple of hashes overlap. And usually you just say if at least one hash is the same, the vectors are close.
And your hash function is the 5 outputs. Just
right. So we say that these two extended LSHs, right, which are all 5, match or determine the close vectors if at least one of them are the same. And here's like I took vectors which are far, and you see non-overlap, and that's what we want. That's just giving you intuition how it works. Okay, this is our building block, and here's our basic construction, basic keyless fuzzy search scheme. And again, it says encryption, but it's really masking. So, and this is how it works. Okay, I'll come here. So, access data, remember that's like the photo I'm looking for. So, I take that and I apply extended LSH, which you know is a collection of this LSH hashes. So I get multiple outputs here, and then I use two hash functions. I use one hash function on each of the output, and these are going to be my tags I'm going to search for. That's what's stored on the server. I apply different hash function to the same outputs, and that gives me secret keys I'm going to use with some standard symmetric encryption scheme to encrypt my record. And I'm going to get multiple ciphertext, and all of that is stored on the server. The server just indexes ciphertext by the tags in whatever B tree or some data structure it uses to index data normally. To query, you do pretty much the same thing. You get the photo, apply LSH, apply the hash, get the tags, send the tags to the server as the query. The server just compares the tags and returns ciphertext whose tag overlap. And then the user can decrypt, because since tag overlaps, it guarantees that at least one key will be the same, and the user can use that key to decrypt the ciphertext. So very simple. And we prove that in the random oracle model, assuming hashes are random oracles, then this scheme satisfies our security definition. Of course, so the leakage function here will contain equality of LSA hashes. That's what's leaked. And also security depends on the entropy in the LSH tags and security of the basic encryption scheme. So, and of course we have to be very careful. It's not that we prove that it's probably secure, everyone should use it. It is probably secure, but it's very important to understand the limitations and the security. So that's why one will, and in the paper we try to discuss the risk associated with using such a scheme, that security is not very strong. And this, especially here, it's not even entropy in the data, which is hard to estimate, but entropy in the LSH tags, which estimating even harder. So that's, of course, a limitation. And what does the leakage function imply? What does equality of the LSA hashes implies? So that's all has to be carefully assessed or studied before schemes like this are used. Okay, very briefly, so the second construction is uses fuzzy extractors. So just to remind, fuzzy extractors, a primitive where you can generate randomness and later reconstruct it, but you need a helper string. The generation algorithm takes some data, generates randomness in the helper string, and later you can reproduce the randomness with the help of the same helper string, and then it will be the same randomness. So this is how we use this construction in our thing. The search is the same. It doesn't use fuzzy extractors. It still use LSH hashing. The tags are computed the same way. But you can use the fuzzy extractor to extract randomness from the data, and the helper string can be stored with the ciphertext. And then the extracted randomness can be used as the key. The only advantage here is that it seems like we can rely on the entropy on the data itself, not the entropy on the output of LSH hashes as before. And you can decrypt similarly because you'll using this reproduction algorithm, because you will have the helper string coming with the ciphertext. So we prove that it's also satisfy our definition because you need but now we can rely on the entropy in the original data, not the entropy in the LSH hashes for security. But we still, of course, need this secure encryption scheme, which is not an issue. But we need a reusable fuzzy extractor here. And unfortunately, there are not that many constructions. The previous constructions had very strong security assumptions. Recently, there was a paper by Canetti et al. Proposing new reusable fuzzy extractors. And interestingly, when we looked closer and took their construction for Hamming distance and instantiated the fuzzy extractor in our scheme, it turns out that we get the exact same scheme as basic LSH. The exact same scheme. And that's interesting. Our first construction had nothing to do with fuzzy extractors, and their fuzzy extractor construction has nothing to do with LSHs, but they do boil down to exact same construction, and our two security proofs will boil down to the exact same assumptions. So interestingly, very close. Okay, so and finally, as I said, since we thought of some applications where this access data images, we wanted to construct and implement a scheme for image search specifically. And so why we cannot use the general scheme? It's only because the existing image search algorithms, they work with feature vectors. So First one takes a photo and image and extracts feature vectors which represent some interesting points in the photo, some shapes, some colors, and so forth. And then closeness is defined in terms of feature vectors, if enough of feature vectors overlap. And two features are close if they have at least one overlapping LSH tag. So it's very close. It just we have to work with feature vectors and not really data images as the whole. And we constructed KLFS for image search. So LSH tags for search as before, but they're extracted from the feature vectors, and feature vectors are extracted from the image. And we encrypt the whole image or the whole data under randomly chosen symmetric key. And we make it so that the key can be reconstructed by anyone knowing enough of closed feature vectors. Therefore, we use the building block secret sharing, where you split the key into multiple parts. Any t shares enough to reconstruct, but any t minus 1 shares give you no information about the key. So we secret share a random key, and one share is per one LSH tag, and then encrypt each share with a key deterministically derived as before from each LSH tag. So I don't have a figure, but I hope you get the intuition. It's really close. And we prove security similarly. It's similar, but we need entropy. So in the LSH tags coming from the feature vectors. And we implemented this. We wanted to test how it works. We implemented the KLFS scheme, and we're working with some recognition benchmarks, which has a collection of images, and you can search. You retrieve images of the same, let's say they had the images of like lamps or guitars taken from different like angles and different lighting, and you see how we do. So what we observed is that efficiency is not an issue. There is not much overhead. You of course need more storage, but I don't think that's an issue. So what's interesting, we found that the parameters, really you have to set up manually, empirically, and this is similar to what the existing image search algorithms do. And this is because LSH bounds construction comes with the parameters. They're really conservative. They're supposed to work for any distribution. But then it really makes sense to tune these parameters for your particular data set. And so the precision and false positives, what we found that again it matches the results for unencrypted search. The only problem is that for unencrypted search, they know how to deal with false positives, which grow quite rapidly. They kind of do fine-tuning after the search is done to eliminate some of false positives. But we cannot quite do it on encrypted data, and that's kind of the main obstacle, and that's what we're still looking how to help this issue. What can be done? And yeah, that's basically it. So we looked at the problem of fuzzy search in the keyless setting. We formalized security, provide several constructions, proved security according to our definition, and in the paper we spent some time kind of explaining the issues why it's still, we don't want people to use it right away because we really want to make sure us and everyone understands the issues coming with using weak security of this sort in practice. We really don't want everyone to jump in, because people hear encryption and security and they think it's good enough, but it may not be good enough, but it's a start. Okay, thank you.
Yeah. So we have time for a few questions. Anybody have questions? Yeah, we can do that.
Concerning your tags, do you think of the tags as having any semantic content?
So we don't want them to have any semantic content. So, and in our case, it's they are like collection of random numbers, except that for various queries, you see that some random numbers are the same. Right, and so the question is, what can attacker infer from this?
So do those random numbers have any relationship, even if it be through the complete encryption process, some relationship to the original data?
The only relationship is that if you make queries for two images which are similar, you will see more random values overlap across these queries. That's only it. It only gives you information more or less close. But that's exactly the point, is it's hard to assess. I cannot tell you, I'm just telling you what's leaked, but I cannot very well say what does it imply exactly, and that's one of the issues here. Yeah.
So in this sort of message-locked encryption thing that they did, so they wanted to get an exact key out of it, and you don't have entropy messages. So one of the solutions they proposed in subsequent work was try to use some sort of oblivious functionality, and then try to make it interactive. Have you thought of something like that regarding the locality-sensitive hash? So the idea being that you have a remote sort of oblivious thing that doesn't give you keys in the setting, but gives you hashes that have your LSH property, and then you can maybe make stronger statements at the cost of like one round of interaction.
Are you talking about this, like employing the services like Pythia and all? What? No.
Something
like this.
I think Pythia is only for keys, but maybe
Right. So we briefly thought about this, but didn't consider it closely. Yeah, one thing I forgot to say, like it makes total sense to use slow hashing, what they use for passwords, because it's okay for one user to retrieve. We don't want the attacker to do a lot.
So the oblivious PRF doesn't immediately solve this problem because you still want to look at it.
Right, and that's pretty much the extent. Right, yeah, that's the extent we've done. Yeah.
Anybody else? All right. Well, thank you very much.